distribution samples refer to the test samples not well covered by the training data, like these black cats. They are misclassified with high confidence due to their black bodies. To explain why these samples are out of distribution, we developed OOD Analyzer, a visual analytics tool which provides an ensemble detection method and a grid-based visualization to detect and analyze out of distribution samples.
In our current work, we visually compare two cohorts of segmented and classified tissue images, originated from single-cell omics data. To that end, we developed data-driven and interactive workflow implemented in a multi-linked view system. Finally, we show the effectiveness of our workflow through specific case studies.
Attention mechanisms have greatly improved the performance of many language models, yet with great power comes increased complexity. In this work, we present attention flows, a visualization that let users interpret the language model's decisions and gain insights into the underlying self-attention mechanism. We also support model comparison that helps to fill the gaps between models in different training stages.
Deep neural networks are vulnerable to maliciously generated adversarial examples. This brings high risk in applying these networks to safety-critical applications. We develop a visual analytics approach to explain the root cause of such wrong predictions. Our contribution contains a constrained data path extraction method, a river-based visualization, and a contribution analysis method.
Data videos are quite popular nowadays. They usually show changes in the data. However, creating a data video requires multiple skills, and the process is usually laborious and iterative. Our approach focuses on automatic and interactive visual enhancement of important changes in time series data with data video.
String graphs are variant of stack graphs with curve-based line, and the main factor affecting its readability is the sign allurance through a perceptual inconsistency of the orthogonal and vertical direction. Aiming at reducing its impacts, we revisited the baseline formulation and proposed the concept of composition to help the string graph layout optimization. The result shows that our algorithms perform better than the others.
Spot SDC is a visualization system that helps researchers understand the resiliency of HPC computation kernels to silent error corruptions. It gives users multiple perspectives of details with different granularity about the impact of SDC on an application's output. It also provides novel insight into how silent error propagates through a program's execution.
We present the first generic design space and library for visual piling. Inspired by physically piling paper documents, visual piling describes an interface for spatial organization of visual artifacts into piles of partially overlapping items. Piling affords interactive grouping, arrangement, previewing, browsing, and aggregation to reduce the complexity and support comparison of large collections of small multiples.
Position is believed to be the most precise encoding channel, but our perception and memory of it can still be biased. Past work has shown that the vertical position of bars in a bar chart is recalled in a biased manner, illustrating both an underestimation and overestimation bias of position. Here we find that the aspect ratios of the bar marks can cause this position bias, specifically resulting in overestimation for bars with wide ratios and underestimation for bars with tall ratios.
Imagine you have tons of text data to analyze. And you want to get an overview of your data, but traditional topping modeling techniques such as LDA are not working for you. Then, why don't you try Architext? We introduced a scalable and flexible way to interactively build hierarchical topics.
We have seen many visualizations for tree data structures, but when showing changes in trees over time, some focus on displaying hierarchy, while others highlight their changes. With split streams, we combined two approaches and their individual benefits. We evaluated our method in a user study and consider it a general-purpose method for the visualization of dynamic hierarchies. Our JavaScript library is openly available.
We asked participants to recreate bar graphs. When the bar was alone, we saw a different pattern of error than when the bar was presented with context in a stacked bar graph. We find that absolute error increased for higher bars when they were presented alone. We also found that there was a bias in the responses such that they were repulsed from an implicit 50% mark. We found a magic number, 10%, to predict error. Participants are usually within 10% of the height of the bar.
CarxS is an authoring system which enables rapid creation of zooming-based scatter plot-like visualizations in just tens of lines of JSON. We contribute a declarative grammar for such visualizations, which captures a large design space. By working with multi-node database spatial indexes, CarxS enables interactive browsing of billions of data points. Come listen to our talk to learn more.
Digital humanities present great opportunities for testing new visualization approaches and evaluation techniques. However, and given the diffuse character and novelty of the field, it may also be intimidating for novel and senior researchers willing to get started in the discipline. In this paper, we propose a data-driven analysis of visualization for the digital humanities to identify key themes, authors, and relevant publications. So if you want to know more, please read our paper.
As commonly known, dimensionality reduction techniques and their interpretations are complex, biased, and uncertain. In drug design, this highly complicates the search for similar and new chemical compounds. To overcome this issue, Canva brings comparison of different molecular descriptors and properties into one tool, featuring planar, 3D, and table views for evaluating the trustworthiness of high-dimensional data projection.
This is a picture of a Tableau visualization within the browser. The data behind the visualization does not exist here, and Tableau is not running. This is just an image. However, parts of this image are fully interactive. Please join our presentation to see how we can share interactive visualizations across the web, free from any dependency on data or visualization application.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Linking and brushing is very useful for interactive visual data exploration. Data-driven brushing tools are getting popular recently and achieve good results, for example the Mahanoda-based brush and the CNN-based brush. However, these brushing tools are optimized by the data from a large number of users, which are not suitable for everyone. In this paper, we introduce an adaptive brush model which takes the user in a loop to improve the brushing accuracy.
Taylor-Coyer flows is a turbulent fluid motion created in the gap between the two rotating cylinders. The traditional reason-based methods are only able to capture the small-scale coherent structure. The detection of the large structure depends on the 2D cross-section, which is not the true configuration. We adapt the feature-level set methods and the density estimation to combine multiple attributes and use them as the filter to separate large and small-scale structure.
Entities and their changing relationships can be modeled more precisely as temporal hypergraphs, but hypergraph models are difficult to explore and refine. By leveraging domain-specific geometric deep learning models and a new multi-level hypergraph visualization, our technique allows for the direct integration of domain knowledge into the machine learning process. The multivariate hypergraph model structure can be analyzed on different abstraction levels. Simultaneously, experts can integrate their domain knowledge on the fly, and then explore the refined machine learning model.
Scatter plots and parallel coordinates are widely used for visualizing multivariate discrete data. However, for multivariate continuous data, the continuous scatter plots and continuous parallel coordinates are more suitable. In this work, we extend them to uncertain data. Additionally, we also extend fibers to uncertain data. If you are interested, come to our presentation.
We present NL4DV, a toolkit that helps prototype natural language interfaces for data visualizations. NL4DV provides a high-level Python API for interpreting natural language queries. The API automates the core tasks of processing natural language queries to infer relevant information and determine appropriate visualizations, allowing visualization developers to focus more on designing and implementing the user interface.
Several recent studies advocated the use of non-parametric density models for the improved characterization of data uncertainty. The non-parametric models, however, present the challenges such as increased memory and computational requirements. In this work, we propose an efficient non-parametric framework for volume rendering in the context of uncertain data and show their effectiveness in classifications via comparisons with the other statistical models.
We present VIS, a tool for visualizing hypergraphs where edges can connect any number of nodes. VIS is the first technique to display hyperedges with no overlap or crossing. Vertices are represented as rows, time periods flow from left to right, and groups can be shown on the left. We designed the layout for readability. VIS shines with mid-size hypergraphs and it allows detailed analysis. We tested VIS successfully using publication datasets and data from historical documents.
As data is changing, our understanding of data should be updated correspondingly. Based on machine learning approaches, we formulate a drift-level index to monitor the evolution of multi-source data, which allows users to capture and reason significant changes from time series data. The proposed visual analytics system is called Concept Explorer. More details can be found in our talk.
We present TransVis, a design study that is proposed to analyze and integrate close and distant reading of multiple translations. TransVis presents the overview of the collection to capture global patterns that is facilitated by the LDAV matrix. TransVis integrates a detailed view to explore interesting path of alignments. We also propose the TLC view to examine and explore the terms of the user selected path to justify and reason the AD analysis.
In this talk, we introduce CallFlow, an interactive visual analysis tool that provides a high-level overview of performance profiles from large-scale samples.
Hi everyone, welcome to LDAV's panel. My name is Julien Tierny. I am a research scientist for the French Center for Scientific Research, and I'm affiliated with Sorbonne University in Paris, France. Along with Dongfang, I am a co-chair of LDAV 2020, and today it's my pleasure to introduce this year's panel. We have today with us a selection of experts in the field of large data analysis and visualization, and they will share with us the current efforts they're doing in this line of research. And since this year marks the 10th edition of LDAV, they will also share their vision about the main achievements of the community over the last decade, as well as future important challenges and how to organize research efforts in that field. So our panel includes Jim Ahrens from Los Alamos, Janine Bennett from Sandia, Andreas Gerndt from the DLR, Ken Moreland from Sandia, and Manish Parashar from Rutgers. And Manish in particular will present his achievements at the NSF and work at the NSF. So each panelist will proceed to a short presentation and we'll take questions in between each presentations. So please don't hesitate to ask questions on Discord and I'll do my best to pass them to the panelist. And so our first panelist is Jim from Los Alamos. So Jim, the floor is yours. Can you hear us, Jim?
Yes, I need the host. I need to share my screen. There we go. All right. Let's try this. Okay, can everybody see that?
Yes.
Great.
Yes.
All right. So very excited about this panel. I like the past, present, and future concept here, and I think it's nice that we're bookended by Manish and I, because I think we'll both give higher level views, and you'll get more details from Janine and Ken and others in the middle. You know, it was nice to go back and think. I think it's good for us to think about what our advances are, give ourselves a pat on the back, talk about what we're doing now, and then talk about what we're going to do next. Okay. So when I was doing this panel, I looked up LDAV 2011, which I couldn't find because there's a 404 link on it, but I found it. I have to fix that. And you know, here's this list of things. I'm not going to make you sort of read through all these things. Instead, I'm going to give you a summary. The summary was that, you know, back in 2011, we were thinking about things like distributed memory, streaming and hierarchy, algorithms, hardware, data management, you know, cognitive, like what tasks are we doing and how can you use that to help you to do large data and then applications. And so, you know, this is a highlight slide that we have for DOE, but I thought it was relevant in the past decade, right? Is that at some level, we got together as a community strongly, you know, national labs, universities, and industry, and we built a pretty strong open source software development model. We had one, but I think things are hardened, tested in a way that they haven't. And I think that's really great. And so, you know, you can see this if you go to this, you know, any supercomputing showroom floor, there's typically some sort of, you know, parallel visualization thing running with application data. And people are out there, and I think we should all feel proud of that. That is, you know, our work, and it's out there and it's working. You know, we've had millions of downloads of software worldwide, and we're handling the world's largest simulations. And I would, you know, extend this beyond DOE. I think it, you know, it's at all sort of U.S. centers and European centers, etc. centers. I think it's really, really good. And the scientists know that, right? You have a quote here from Steve Langer at Livermore, right? We rely on this software. They're running the massive sims, and you know, and it works. And you know, but look at the timeline, right? So the first open source release of BTK was in 1993. That was a couple of decades to sort of solidify things and get things to the point where, you know, you're doing a trillion cell data set, and I think we're doing that routinely. So then I went to 2020, and I looked and I saw what the call for papers was. And my argument here is we had a lot more to say. So certainly in 2020, there was a lot more text written, but if you go in the text and you look at it, you know, it's distributed memory, streaming hierarchy, etc. But a couple of new things, parallel threading, in situ, and increasing scope. And I think the increasing scope is great and sort of represents that we probably have the top box at least handled in some way. That we can do things, and therefore we can increase our scope and think about different domain areas and work from there. So one of the things that's interesting to ask the question is well, why would we add data parallelism and threading? And so the chart on the right shows microprocessor trend data, and in particular, as you're looking at the timeline there, if you look between 2010 and 2020, the big change in hardware is that the number of logical cores went up by a couple orders of magnitude, right? And that is essentially GPUs. And similarly on the right, you know, CPUs are, you know, if you want to compute sort of with peak memory bandwidth and peak double precision, you're probably using a GPU. And so therefore we had to adjust our tools, something that we saw a little bit in 2010, say, but wasn't right there. Now it's just right in front of us, and we need to make sure we're working really well on these machines. And so, you know, you'll hear more about that in Ken's talk for BTK. For in terms of, you know, why in situ, well, we've been working on this. You know, we knew that there was a latency between cores and storage, but as we go to things like exascale, the amount of data that we can generate on node really quickly, it just totally outstrips our ability to do network and storage, and therefore we can't store everything, and that leads to in situ. So that's the difference between the top of the pyramid and the bottom of the pyramid. One thing that's really interesting to me about in situ is it brings up a lot of philosophical questions about the process of visualization itself, because you're thinking about doing things automatically. And so it really actually, I think, leads us into an interesting research space to think about, okay, well, I want to, it gets at sort of the heart of the scientific question. What does somebody want to look at? What would you show them? You really don't have a lot of control over it. So you need to be looking at things and thinking, you need to be doing some automated analysis and figuring out what's interesting. Okay. And so that brings us to this second side of the pipeline where we started adding in these different ways of doing in situ analysis, thinking about things like post-processing. Can we do interesting exploration in post-processing sense? We saw a nice talk by Jonas today about cinema. Can we, how performant are we? Can we be portable as these in situ interfaces proliferate? Can we do portability? That's what Sensei's looking at. And then how do we get threaded performance and distributed memory performance? Okay. So I am the exascale computing project lead for the data in this area. There are a number of projects, not all of them are listed here. I tried to get many of them on though. In particular, there's a project called Alpine, which looks at both infrastructure and algorithms for in situ analysis. Alpine is a lightweight in situ infrastructure. Visit and Fairview also have in situ infrastructures, as well as Sensei looks at trying to make a portable infrastructure so that people can, so that scientists can write a portable way of accessing these different infrastructures. There's in situ algorithms. In particular, when you're doing in situ algorithms, you need to be thinking about data triage. You have to get rid of a lot of the data. So you're able to make some decisions at that point. You might make a representational change. You might do compression as evidenced by like the ZFP library and the SC library for floating point collection libraries. One thing I would say again, change of the decade, right? If you ask somebody, you ask an application scientist in 2011 if they would lossily compress their data, they would laugh at you. And today we have people sort of knocking at our door going, what can you do for us, right? So it's changed. We talked about cinema, and I think data management plays a huge role in this. And one of the nice things about this particular project area is all these pieces are together, both the storage and the visualization are together. And I see more and more, as we become IO bound, we have to think about how we work really closely with the data management folks to solve problems. And you can see good examples of this in the audios. Okay, let's see. So diving down a little into in situ algorithms. There's work in Alpine. So one of the things about in situ is it's not your typical visualization operators that you've had in post-processing. We need to start thinking about new ways of doing things. So you might do things like adaptively sample your data for data reduction. You might put things in a statistical representation, like just use a statistical notion of your data and then see if you can do some feature extraction after the case. We might do things like machine learning, and I believe Janine's going to talk about this more. You saw some work earlier today in the LDAV talk about topological analysis. Again, sort of higher level analysis, and a shout out here too to the TTK folks who have been adding, topological algorithms and thinking about things. Just, at some level, this is a higher level. As we succeed at the lower levels, we can make higher level decisions and higher level concepts that will help people to analyze their data. Hank Childs and company are doing optimal viewpoint selection. All these things, optimal viewpoints, just the tip of the iceberg. You have to think about all, sort of setting all the parameters to get a smart visualization going. And so viewpoint's a good place to start. In addition, there's things like asynchrony you have to worry about. There's task-based runtimes, different models for different programming models for computing things. And so we have some work as well looking at trying to interface to those models. All right, so what's next? The exascale project will complete in the first third of the decade. We will have a vibrant data visualization and exascale ecosystem. One thing I I think I showed it, but essentially e4s.io contains some of the software that we have, and works together, testing, software engineering, dependencies, etc. And that's just going to get better and better over time. It'll be performant. It will have the initial starting point of an in situ workflow, and it'll be integrated with applications. I'll give a shout out there to the Pantheon project led by David Rogers, the idea is to sort of integrate applications. So we take open source exascale applications and pair them with data management and visualization activities. Those would be good starting points for research because they're all open source and ready to go. So they will run on supercomputers. They will have input decks that make sense. The next big challenge is we see it, there's this increase in scope. I won't talk too much about that. I do want to talk about, personally, I think this automation for in situ and in general, the concept of automation for visualization is sort of a fundamental thing you want to think about because it really does get at the heart of what we're trying to do. How do you make a decision? Machine learning will probably play a role in that as well as optimization. Moore's law's almost over. It's one of those things that's still dying, but there will be custom hardware, and you see this in things like the machine learning hardware, specific machine learning hardware, and other ray tracing hardware, et cetera. You'll see papers on taking advantage of that, as well as I think hardening software for streaming and asynchrony, which has been out there for a while, but I don't think it's been hardened as other pieces have. Finally, what's next? And these are my own opinions, not saying anything, special here. I think it's really data for science. I think that a lot of people think it's going to be an AI call. I don't think it's going to be an AI call that replaces exascale. I think it's going to be a data call. And a good example of this is, you saw it in real time, right? What's the pandemic data response? You have things where you have real-time data coming in, you have HPC models, you have verification and validation going on in real time. And I think that's the kind of thing that's going to get somebody's interest and sort of drive the community forward. You can see a small call on the right that was in Mark Cohen's deck for DOE, but I think that it'll be much bigger than that once they come to the point where they have to make some decisions. And I'm out. Thank you.
All right, thank you very much, Jim, for your presentation. So do we have questions for Jim? And here I'm inviting the other panelists to jump in if you want to react to Jim's presentation. We have a couple minutes, some time for questions. Maybe I can start with one quick question for Jim. At some point, you mentioned that one of the among the big things that you saw coming over the last decade was the increase in scope. And you mentioned several themes, including InfoVis. Is it something that you are involved with in Los Alamos?
Yeah, so one aspect is experimental science. So if you think about these big accelerators and light sources, right? They're generating data real time. They have a few days to do an experiment. They generate things, and then you want models. So the way it links back to HPC is you want the models to run real time too. So essentially, think about getting data from an experiment, then you want to sort of dynamically validate that with the experiment while it's running, and have that both guide people and then tell people when it's wrong. Like, oh, we were modeling this, but look, we actually found some really interesting phenomena that's going on here. And you might change your control of the experiment while you're going. We had a recent LDRD project on that, and I've seen some interesting work in that area.
All right, thank you very much. So I think in the interest of time, we'll switch right now to Janine's presentation, and we'll also have a short session of questions and remarks after the presentation. Thank you.
Okay, can you hear me okay?
Yes.
Okay. Well, thank you for inviting me to participate today. I was really excited to hear about the topics. I think this is a really timely panel, and I'm happy to participate, so thank you. So I wanted to start talking today and give you, just a little bit of background and an introduction to me and who I am, because I think that really, and where I work, that really frames my perspective on what our accomplishments are as a community, as well as what I think those opportunities are going forward. So very briefly, I work at Sandia National Labs. I'm a manager there. And Sandia is an engineering laboratory, and we serve a number of missions. So one is, we are a National Nuclear Security Administration laboratory. So we do a lot of work with the ASC program there, And I also have done a lot of work supporting the Office of Science. And so, just so that you have a context about the types of mission spaces that we support on the NNSA side, we're really looking at analyzing and predicting the performance and safety and reliability of nuclear weapons and to certify their functionality in the absence of nuclear testing. And then on the Office of Science side, we're really looking a lot more often at exploratory science workflows. So there we're looking to deliver the scientific discoveries, capabilities, and major scientific tools to transform the understanding of nature. So both
I'm
of
sorry,
these—
Janine?
Yeah?
I'm sorry to interrupt. We're seeing your first slide at the moment. Are you still on the first slide?
I'm on the second slide. Do you? But not.
Maybe you're sharing the presenter. We see the
Here,
actual PowerPoint window. Sorry for the interruption.
No, that's okay. So if I go here, which slide do you see right now?
We see the PowerPoint window.
Okay, so there's got to be a way to quickly swap, right? Is it one of these? No. So are you still seeing the PowerPoint window?
Absolutely. For me, yes.
Are you seeing the screen notes? Or the presenter view? Or are you seeing?
We're seeing the main
view or the slides. We're seeing the GUI. Oh, well, there's.
Oh, there you go.
There it might have been latency. Okay, this was the slide where it was. Do you see a slide with a picture of Sandia and NSA and Department of Energy?
Absolutely.
Okay.
Okay. Thank you.
So then I have
Sorry.
these two mission statements, right? And so I think the key thing about the reason why I'm sharing this is a lot of the work that we do is very mission oriented here. And a lot of my research interests come in looking at how we do foundational and make foundational research advancements and actually deploy those on mission problems. And so I've been at Sandia for 11 years now, and from 2009 to 2017, I was a staff member focusing on a number of technical challenges, looking at how to track features of interest, how to do that in situ. And then I also had more of an HPC focus for a portion of that, looking at how to write productive portable performance software for next generation hardware. So looking kind of broadly at the entire ecosystem as a whole. Over the last few years, I've been taking a more programmatic view. I have a different role now as a manager. So I manage a team of around 20 staff and postdocs, and they're focused on two different areas. One is data science, where I connect to the in situ community, and then I also manage a cohort of quantum information scientists. My responsibilities are a bit more programmatic in nature, so working to shape Sandia's research investments and strategy. And then I've also continued to stay involved in the broader HPC communities. And so part of the reason why I share all this is, that impacts the lens on which I look at these, accomplishments, opportunities, and challenges going forward. And so, when I think about the accomplishments that the community has had over the last 10 years, right, I think a lot in terms of this tool called the technology readiness level, right? This is a tool that a lot of government agencies use to talk about the advancement of, foundational research all the way to deployment. And so when I think about the accomplishments the LDAV community has had over the last 10 years, I think about it in this space, and you can see that there's been, just if you look at the conferences, as Jim alluded to in his presentation, you go to the SC floor, you see, all kinds of, VIS and analysis, new research advances that are focused on exascale ready algorithms and infrastructure. You've seen these within LDAV, VIS itself, and workshops like ISAF. So there's been a tremendous amount of accomplishments that we've had at this low TRL space. I think we've made some really significant tractable progress productizing exascale ready tools. And again, Jim talked about some of this in his presentation, right? Alpine and the whole ecosystem of tools that exist within the DOE community. And so, it's exciting to see those being brought to bear as, we're getting ready for these exascale systems as we see them get ready to land. And then on the far right, again, Jim and I had a similar perspective here. I think we've really seen an application adoption of those productized post hoc tools that have been developed. And I think there's some really awesome accomplishments that we have seen that have been funded through things like the SIDAC Center. And when I look at how our ASC program is using the post hoc tools, you have the new staff coming online, they know how to use it, they're familiar with it, and it's an everyday part of their workflows. And so I think that's really exciting to see. So now shifting, to what is the current view, what are current opportunities as well as future opportunities. I started thinking about this, and I, wanted to use the DOE Office of Science initiatives as kind of a bellwether for opportunities, right? So the Office of Science isn't the only funding agency. However, they have a number of ongoing and new research initiatives. And I think it's really interesting to think about how the LDAV community is positioned to have impact in each of these spaces. And also look at the funding trends, because that tells you where things are, where they're going. There's always great ideas, but if you don't have money to support them, then it can be really tough to actually deliver. So I'll be talking a little bit about each of these in the next slide. And so looking across them, the ones highlighted in blue are the ones where I really see some opportunities for the LDAV community to have impact. So exascale computing, I think this is a place where we have tremendous opportunity now and in the continued future. When we look at the funding trends, right, they're high sustained funding, although, they're starting to decline, and it's unclear what it'll look like after 2023. That said, a lot of the opportunities I see in this space, the ongoing and future opportunities, are at that higher end of the technology readiness level spectrum, right? It's in productizing and deploying those exascale ready tools with a focus on things like performance portability, integration within the broader ecosystem of tools. How do we make sure we're leveraging all the hardware and software advancements that are happening across the hardware software stack, and really making sure we're engaging with the application developers. That means making sure our tools are usable, making sure we have training and everything for those folks. And along those same lines, I'd see there, this is less of an opportunity, but more of a need, is to enable with the facility folks to make sure that the policies that they have for reservation and jobs are compatible with some of the new ways we're thinking about in situ workflow. So just forward leaning, if we want to, we're developing all these cool technologies, if we want to make sure that those are going to work on those future ECP or, exascale computing platforms, we need to make sure our job reservation systems support some of the different ways of launching jobs that we see in some of these in-situ systems. So that's kind of, I think, where we are in terms of exascale, and this is one of the more current opportunities. Going forward, I also see some opportunities in quantum information science. And if you had asked me a couple of years ago before I started managing a quantum team, I would have thought, oh my gosh, how could, quantum computers don't exist. How do we ever have impact there? Like it's too early to even start thinking about that. But one of the things that I've been learning about is that, there are these what are called noisy intermediate scale quantum systems. They're called NISQ systems. And they're these early quantum computers that will be deployed akin to how GPUs are deployed. So as accelerators in a hybrid quantum classical computational setting. And so right now that quantum computing research area is really focused less on what we can do with the quantum computer, but they're starting to analyze the behavior of the NISQ system itself. And when we think about what the system is, it's a high dimensional, noisy, dynamic system. It requires in situ analysis tools. You need to be observing what's going on, doing calibration, all of these things real time as the NISQ system is operating. And so while it's not immediately obvious how we can bring our tools to bear, we have in situ tools, we have analysis algorithms for looking at high dimensional noisy data. And I think there's a tremendous amount of opportunity to start interacting with some of these folks who are doing this quantum information science And we also see some increasing funding trends in this space, and so there's some opportunity to engage there more broadly. And I think it's through that early engagement in these, low TRL tools that we can start to really understand what the role of data analysis and VIS is longer term in the longer term quantum setting. AI and ML, that is also an increasing funding trend. And I think, the LDAV community in particular is poised to address some of those data challenges that are posed uniquely by science problems. So science data is very different than industry data. When you think about industry data, it's narrow and long, meaning you have many samples, but each sample is small. And when you think about simulation and experiment data, it's wide and short, right? Each sample is really big. Each simulation generates massive amounts of data. Experiments may generate a ton of data, but we can only afford to do a few of them. So how can we analyze and glean insights from that big data, make it tractable in these settings, and then take what we've learned to mitigate the challenges of only having a few samples? That's kind of where I see some opportunity on the AI/ML side. I think there's some opportunities in terms of physics-informed AI for high consequence decisions, right? We hear people talking about credibility, explainability, trust of the AI model itself, and that demands kind of an analysis and understanding of that AI model. And so there may be some really interesting ways to bring our analysis tools to bear in establishing credibility of AI models. And then when I think about extrapolation detection, right, we do a lot of training of ML models. And then, if you're actually deploying it and you have an observation, how do you know when it's too far outside the training space? And again, this is, high dimensional data clustering. There are tools that this community has developed that may pertain in this additional setting. And again, funding trends are up and to the right, and maybe some more opportunity in this space. And the last thing that I'll try and quickly summarize is there's an initial investment request in integrated computational and data infrastructure for scientific discovery. And so here I see there being some opportunities for us to look on the in situ data management side of things. How can we apply in situ data management tools and algorithms across a variety of platforms and scales? So here, edge computing, sensor systems, including HPC. How do we make sure all those tools that we have there are composable? How do we ensure they're easy to use by the various users across these settings? So that's kind of what I have in terms of opportunities.
All right. Well, thank you very much, Janine, for this very interesting presentation. So again, if the members of the panel want to interact or comment on what Janine presented, please don't hesitate to open your microphone.
I have a question, actually. Andreas speaking.
Yes.
We are also at DLR, we are also very interested in quantum computing, but we expect to have some working machines. I mean, there are some first machines available. You can play with it. Just small use cases can be executed, but they are not really ready for huge computation models also, or for problems. And you mentioned noisy intermediate scale quantum systems. We expect that quantum computers maybe are available as a usable machine in 20, 30 years. Do you expect to have your NISQ systems earlier?
So at Sandia, we have quite a few, we're investigating quite a few technologies, and we have something called the Quantum Performance Laboratory, where they're looking at characterizing and benchmarking existing NISQ systems. And so we are really fortunate to have direct access to the people who are developing these here at Sandia, developing these systems, and the experimentalists and the theoreticians. For the broader community, I think there's opportunities to engage through collaboration, and there are other national labs who are doing similar types of things within the United States. And in particular, there were several national quantum initiative related centers that were funded by the DOE this last year. And I think that's a nice opportunity for people at universities and elsewhere to engage. But you're right, general purpose ones that are broadly available for public use are not going to be online soon. But I think there's opportunities to engage in the national lab settings through these initiatives via collaborations earlier on.
All right, well, thank you very much, Janine. I suggest we move on now with the intervention of Ken. Ken, would you be ready to share your presentation?
I could be. I thought Andreas was going to go before me, but I'm happy to go next. If
Oh, I'm sorry. I'm sorry. Actually, that might be my bad. You are absolutely right. I'm sorry. Andreas, would you be ready to share your slides?
Yeah, let me check. So here it is.
Thanks, Ken.
So can you see my slides?
We can see them. The aspect ratio is wide indeed, but maybe when
yeah,
you
sorry. So I mentioned that. So I have a nice wide screen, but hopefully you can see the slides. All right. So can I go ahead?
Yes.
Yeah.
I think.
Okay. My name is Andreas Gerndt.
Sure.
So I'm with the German Aerospace Center. I'm also coordinator of the VESTEC project, and VESTEC is an EU-funded project about, let me say, new HPC use modes in the exascale domain. But first of all, I want to come back to the technical advances. So Julien asked for that. And maybe it's not surprising that I have pretty the same points on my list. So first of all, I think over the last 10 years, especially in situ coprocessing, is one of the big topics, and it is a need if we consider to go forward to exascale. Without coprocessing, we cannot process the data, we cannot visualize the data. Maybe it's just shortcuts also, but in general, there's no possibility to go beyond of that. But not all simulation codes really scale well for exascale. And maybe it is not a need for all the simulation codes. For instance, for weather forecast, maybe it is not really needed to go into the exascale domain, but to come up with ensemble simulations. So this is the second point on my list. Ensembles are very important to change some input parameters and to show variation in the simulation. At the end, to come up with uncertainties in the data sets. So for me, it's very important to show that science does not talk about the truth, but can just give hints how a situation would evolve. And uncertainty is very important. So consider the COVID-19 story. So also the scientific community had some issues with that. And it is very important to come up with the right answers to the stakeholders like politicians and also to the public, what the trends are, not what the truth is. So we cannot talk about that, and a simulation cannot really present the truth. So with uncertainty, we have, like depicted here by Mark Rautenhaus, 2015, we can also give some hints what is most probable. So these probability fields are depicted here, and this is what maybe we can communicate to the public. And the fourth point here on my list is mature standards and tools. I really like the situation that the tools developed over the last 10 years are now available. Almost all the results presented by the community is now open source and available also for people which are not so deep in HPC or parallel visualization, but they can go ahead with the tools, and this is definitely a plus over the last 10 years. So for the next decades, maybe, I think machine learning could become a big topic. Maybe you would say, okay, this is already a big topic, but consider the simulation of weather forecasts or climate change simulations. So they rely on the knowledge of the engineers. They put their knowledge into the models. They couple the models, and then they simulate ensembles about the climate change. But we have also plenty of new missions, Earth observation missions, and these information should also brought to the models. And here I believe we have to apply machine learning to classify what comes from satellites, identify what is not known so far, and to enrich the models for the simulations. Yeah, and the last point here on the list is interactive supercomputing. It is not just because I'm a virtual reality guy, so I want to interact with the data. This is also an interaction, but also the high velocity data from satellites, but also from social media, all such kind of information should somehow guide the supercomputer and the supercomputing. And this is what I call interactive supercomputing. And interactive supercomputing is actually what VESTEC is about. So look at the right-hand side of this slide. You can see the operation room at the DLR, at a center for satellite-based crisis information. So they receive high velocity real-time data from satellites, maybe from field, and then they have to analyze if there's an incident, if there's an earthquake, a flooding, a wildfire, and then they have to go into action and have to help the people in the field. Here, we want to bring in also high performance computing. We want to support them with more reliable prediction. But this is not just about natural risks, as depicted here on the right-hand side. The experts are here at the Center for Satellite-Based Crisis Information. But we also want to address, with VESTEC, we also want to address other use cases like critical clinical diagnostics or spread of diseases. I mean, Corona is one example, but we started already 2 years ago, so we had no clue about Corona, but we already addressed a spread of diseases. And we brought in 3 use cases. They are depicted here. So the first use case is about the wildfire monitoring, very important use case. Last year, we had the huge wildfires in Australia. Right now, we have the huge wildfires in California and Oregon, but also in Europe, it becomes more and more critical also for northern parts of Europe. Wildfires has to be monitored. There's climate change, and therefore wildfires becomes more and more an issue. The second use case we address is mosquito-borne disease. So I mentioned the Corona was not in view as we started with VESTEC, but mosquito-borne diseases is a well-known use case. So we know exactly what kind of data input is used to analyze the spread of diseases. So right now, still we have plenty of issues to understand the spread of Corona, actually. Both use cases are linked to high resolution weather forecasts. They need very precise forecasts for the weather situation, for the specific domains or for the specific region they aimed at. The last use case we address is the space weather. It's different weather, it's the space weather, but it's also very important if such kind of incident happens, the technical supply chain can be affected, and therefore we selected that as the third use case. Okay, and I think we have a pretty wide field of use cases so that we can evaluate our workflow, which is depicted here. So you see that on the right-hand side on the picture. At the beginning, we have a sensor network, we have social network, so they trigger the simulation. But we are at that first triggering, we are not interested to receive very precise simulation. We need, as quick as possible, we need some information about the situation so that we can offer such kind of information to the crisis manager. The crisis manager then can immediately guide the forces in the fields, and then the forces in the fields can become also sensors, some kind of a sensor for the simulation. And whenever some input parameters changes, the simulation has to be modified or has thrown away, and we have to start new simulations. We have to spread some additional simulations, and we have always to inform the crisis manager as soon as possible. The crisis manager can analyze the data and can also set some new hotspots also for the simulation, and then we have also some interaction by the crisis manager. And so this is the idea behind the workflow of VESTEC. You see, it's highly interactive. So after the simulation, we start the in situ part. Very important here as well is we do not want to store data at all. So we have to process the data when it flows through the supercomputer. And our idea is to carry out topology feature extraction to identify the core features. So we do not need all the exascale of information. We need just the core information for the decision maker. So the essential information has to be extracted, and we believe that topology information could be the right approach. So we integrate topology, the topology toolkit. Julien is the partner here on that, and we over time, if we have more than just one time step, we can also sample the data over time and everything in situ. So we do not have to store data at all. Thereafter, we receive some kind of a skeleton data set, which can then be forwarded to a data analytics group to analyze the data, to analyze the topology skeleton, let me say, and to extract the most representative in ensembles. So this can be then forwarded to the crisis manager. The second part here is by Intel. So they brought in their Osprey renderer, and this is also very important. So on the first hand side, we reduce the data extremely. On the other hand, we also need enhanced perception on the in the crisis management center, and this enhances situational awareness. And here we want to evaluate how Osprey and ray tracing can support. Okay, at the end, everything which comes to the crisis management center, and here we have applications. So in the first place, we want to come up with the tools developed by the community. For instance, ParaView. So ParaView is a general tool, so can visualize all the data which comes in, but it is not tailored to a certain application. Therefore, we have a second application, which is a wildfire analyst. This is a commercial tool. TechnoSilver is a company on that, and they try to enhance their application, and they want to evaluate if that what we extract is really useful for the decision making. We also think about that the persistent diagrams could be directly accessible to the decision makers, so that they have a complete new approach to information, let me say some kind of information visualization, so that they get a better impression about the uncertainty and the probabilities of that what we are presenting. The third toolkit is Cosmos Scout VR. It's a toolkit which maps all the Earth Observation Center, also other planetary data, Earth system data can be explored interactively with that tool, also in virtual reality, but also virtual reality has to be tested if it is really appropriate for urgent decision making. This is the end of the workflow we have in mind with VESTEC. This was just a short overview of VESTEC. We've organized also an urgent HPC workshop at the Supercomputing 2020. It goes also virtually if you are interested to participate. So maybe in 3 or 4 weeks, we have this workshop online. Okay, thank you very much.
All right. Thank you very much, Andreas, for this very nice presentation. If we have questions from the attendees or the panelists, please feel free to open your microphone or ask a question on Discord. Maybe I can start with a quick question for Andreas. So you mentioned at some point the interactive supercomputing aspect that is central to VESTEC. And you also mentioned the urgent decision-making application, which is also central to the applications. And it seems that it opens new perspectives for urgent HPC, where basically the analysis will need to be run in a sort of best effort kind of process. And I wondered if you could tell us more about this.
Yeah, okay. I had just 10 minutes, so I skipped some of my slides. For instance, the problem we have to address with supercomputers, HPC. So in general, the HPC community still relies on schedulers. So whenever we want to have such kind of a workflow depicted, so we have to open up the paradigm to get access to the resources. But then we have also aspects of security. How can we protect that? Also, how I address the stakeholders. So how can we really guarantee that we have resources when it comes to an incident? So if we have a wildfire and there's just a big simulation running on one of the tier 1 supercomputers in Europe, and we do not have processors left, so what should we do? Should we wait until the supernova simulation is done? So there has to be some kind of a policy, and therefore we need to get access to the governmental level to find a way so that we have a system which always guarantees resources, so that whenever we have such kind of an incident, that we can start the analysis and we can support the urgent decision makers. And it doesn't matter where the supercomputers are. In general, the workflow is open. If you do not have a higher requirement on the final bandwidth from the supercomputing center to the urgent decision making center, could be somewhere, could be in a different country. You have to reduce the bandwidth, and then it doesn't matter if you do not have direct access to your local supercomputing center. Yeah. So, but it's up to a governmental decision.
Okay. Well, thank you very much. And I guess, of course, there is the Discord channel and server that is available all week. So if attendees have more questions or want to interact on a one-to-one basis with the panelists afterwards, please don't hesitate to use the Discord server for that. So thank you again, Andreas, for this great presentation. And I suggest to move on now. So with Ken, could you share your screens?
Okay, I see.
Oh, there we go. Okay.
Sorry.
All right, can you see that? Okay.
Absolutely.
Great.
Thank you very much.
And I'm now at the next slide. Can you see that too? Awesome, it actually worked. All right, thank you. My name is Ken Moreland from Sandia National Laboratories. My background is, I've been working in the DOE for about 20 years in large-scale scientific visualization. Currently what I've been working on is this large exascale computing project that Jim is also working on. And so, my thoughts for the panel are pretty, well framed around that. And so that sort of, really molded how these slides came out. The first thing that we're asked as panelists is our view on the advances of the last decade. So, I'll start by talking about, how we got here. And this is actually the same slide that Jim showed earlier. The idea and the same idea that Jim said is that, the VIS groups at DOE have been really focused on providing tools for practitioners that are running simulations on the largest HPC computers in the world. That raises difficult VIS problems. And those problems themselves need high performance computing to solve. I think we've been quite successful. Our groups collectively are leading visualization analysis for DOE scientists, as well as other scientists. Our tools are installed and used worldwide on HPC installations, both inside and outside the DOE. We have millions of software downloads worldwide, collectively of all these tools. But really the important part is that it creates the capability for DOE to look at data from the world's largest simulations. And that's something that DOE really pushes is impact, that, we can't do VIS in a bubble. We really have to push it to, to practitioners who will actually be using these tools. And that brings us to kind of what our current challenges are, what we're doing now in VIS. While we're preparing for the exascale, our visualization groups within the DOE had identified 3 major technology gaps. And I'm not claiming that these are the only technology gaps that exist today, or at least existed 4 years ago when we started. There are certainly others, but these were the ones that we valued as most critical, in that if we did not solve these, we would not be able to do data discovery at the exascale. So the 3 things are: first, we recognize that the processor technology for HPC systems is changing dramatically. We're moving from general purpose CPUs to more specialized GPUs and other accelerator technologies. Second, we recognize that file IO limitations require in situ data reduction and visualization processing. And as a follow-on to the second problem, the third problem is that in situ processing in turn changes the dynamic of how we interact with data, and that necessitates new methods of analysis and visualization. So I'm really going to focus on this first issue of changing in processor technology. That's the major focus of my work. I know Jim and others have talked a lot about the other 2, about in situ technologies, as well as interaction technologies such as cinema and things of that nature. And of course, we've all seen that earlier today at LDAV as well. So why did the change in processors matter so much? Because we were doing parallel computing for like a long time before we even started thinking about exascale. And this is an old slide, but I like it because it visually compares the difference between a CPU and a GPU by just looking at their dies. If you look at a core and a CPU, it embeds about a half a century of technology, of research and development that's gone into making your code run fast. The GPU basically throws most of that away and replaces it with raw arithmetic units. So that gives you, a really high, flop rate, but you really need to structure your program correctly for this type of device, or it's just not going to run well at all. So LDAV problems can definitely benefit from this raw power, but it requires a careful restructuring of code to run efficiently. So this is a problem that the DOE community has been working on for about a decade now. In the early part of the decade, established the fundamental research for the problem. The current efforts are contributing to a combined software project named VTKM. And the VTKM library is a central implementation of accelerator-based VIS for applications within DOE. One of the big challenges of software in this new HPC realm is that it has to be used across many HPC installations, or at least we in the DOE care about it being used in lots of different HPC installations, which means it has to be very flexible. So in the past, this flexibility wasn't that difficult because there's a lot of compatibility across CPU processors. So even processors from different vendors, sometimes they shared instruction sets like the x86, but even when they didn't, there were equivalent compilers for each architecture, right? So if you had a program written in C++ or Fortran, it could be compiled pretty much anywhere. This is just not true anymore. We're in a completely different environment. Each vendor has completely different instruction sets. Each vendor provides different compilers with different programming models. And even when one vendor tries to emulate the model of another vendor, there's always some idiosyncrasies of non-portability between the two. And then on top of that, each vendor has these proprietary structures that changes the behavior of how programs run. And so it's just too much to attempt to try to write every visualization algorithm multiple times for each of these architectures. And so one of the challenges of VTKM was to provide a write once, run everywhere framework. So we've figured out basically how to do that. The trick, there's multiple tricks to it, but the fundamental thing you have to do is break your problem into lots of little bits that can be run independently or at least semi-independently. And so fortunately, this is pretty feasible, at least in large scale VIS, because we operate in structures like finite meshes that already comprise lots of little pieces. And so we achieve this in VTKM by providing several ways to break up meshes into its constituent elements, and then recombining those elements after you've run your independent or semi-independent algorithm on each one of these pieces in parallel. So I'm going to end by speculating on some of the the real challenges that we're going to face in the next 10 years, which I think is kind of the interesting part of this panel. So I'll spend most of my time there. And again, thinking sort of along the lines of supporting scientists running the largest HPC systems, what is going to be the next thing? And so let's assume we get to exascale, and I'm sure we will. We're going to be successful for that. But let's further assume that we push to zetascale. And actually, that's a bit less clear whether there's going to be a push to zetascale. There might not be, but we'll probably continue to advance the architecture into faster and faster things. It might be a slower push. What would a zetascale machine look like? Well, it's going to have to be very super power efficient by today's standards. And this is actually something that we said when we were standing at petascale looking at exascales, like, wow, it's going to have to be super power efficient to work. And we were right, it did, and that's why we're dealing with these GPU accelerators right now, is because it gives you much better flop to watt ratio. But we're going to have to do that again, and we're going to have to do that with even more exotic architectures. And what are these architectures going to look like? And I think one of the best things that we can do is look at today's green technology for HPC. So there's an entire subgenre of HPC that looks at green computing. And they have their special top 500 lists that are really measuring watt to flop ratios. And the kinds of things that they're doing to achieve that are using technologies like tensor cores. And for those of you who haven't heard tensor cores, they're basically special arithmetic units or instructions that operate in small matrices, like 4x4 matrices or maybe 16x16 matrices. So they can do that really fast. And the reason why we have those is because they turn out to be very good for deep neural networks. And because they're good for deep neural networks, people are applying deep neural networks for new things, which is causing more demand for the hardware, which is creating this virtuous cycle between the hardware and applications. And so they've come along. There are lots of different hardware that's available today. The question is, what can we do with it? And to the best of my knowledge, nobody's really looked at what we can do with those for VIS algorithms, but I suspect that they could be used for a lot of things. And so this is some possible low-hanging fruit for research. There's also reduced precision. So you can actually get to an exascale on today's machines by just doing 16-bit floating point operations. They're much more power efficient and they're much faster. It seems reasonable that we could take advantage of that because a lot of his algorithms are often just good enough. I mean, really, how precise is marching cubes really? But that's something that we have to understand really well, is that where are we cutting corners? And where can and can't we take advantage of that? Because we just don't want to do something that turns out to be wrong. And also there's kind of a scaling issue where the mantises won't line up if you're getting data from like a 64-bit float and trying to use a 16-bit float. More exotic technologies are FPGAs. The DOE hasn't really looked at that as far as I know, but other HPC centers are looking at that. And the question is, will our current approaches map to FPGAs? And be honest, I don't know. And how well VIS will work on an FPGA probably depends on if we can achieve a good enough compute to burn ratio. So you burn something with FPGA, you want to run enough stuff to make it worthwhile to spend the energy and time to burn it. If you're doing something like rendering and you're rendering a lot of frames, probably you could achieve that. Doing a single contour, probably not. So I think it really depends on what you're doing with those. And that might change how we use visualization. I am going to kind of wrap up because I'm sort of out of time. I'm just going to skip over the fact that we can also look at beyond Moore's law technology, and I think things are really things are very interesting but very introductory there. I think those technologies are going to be like a good 10 years before we even have to start thinking about any practical application of that. But I think these would be really fun, at this time, pure research projects, is that we won't really, you can do something, we won't know if it'll ever be practical, but it'll be an interesting way to build what's going to be done in the future, in the far future. And that's over my 10 minutes, and I'll go ahead and answer questions if there's any.
All right, thank you very much, Ken, for this very nice presentation. So again, if you have questions, please don't hesitate to open your microphone or to type the question in Discord. I'll probably go ahead and ask you a quick question, Ken. You mentioned among the opportunities green computing. mentioning power efficient infrastructures. And I wondered if the challenge was not necessarily to reduce the power consumption, but more to control it. You know, to be able to have trade-offs sometimes to increase the power consumption in the interest of computation efficiency and the other way around.
Yeah, so I've seen research on that level. At the beginning of the Xscale project, there was a lot of talk about designing software to be power aware. I don't think that's really come to fruition, although there may be something to it. And the most successful stuff I've seen is the idea that I can drop the clock rate, save some power, and still actually compute pretty well. So I can drop the clock rate by half, you know, reduce the power by, you know, a third, and I still can run at 3/4 the time because, you know, most of my time was bottlenecked on the memory anyway. So there is that aspect, but I think the hardware folks who build these things sort of want to, you know, provide the solution for us. My suspicion is that what will happen in the near future, because we can't make transistors any smaller, is as the technology becomes better, we'll put more of it on a die, and we'll start creating these specialized units like tensor cores, and we'll let it go dark when you're not using it. So, you know, if you try to energize the entire core, you'd probably fry it because you'd be sending so much power to it. But in a practical setting, you know, the hardware wouldn't let you do that. You just decide what part of the CPU you're using, and the rest of it just won't be activated. So again, my suspicion, and gosh, I hope people disagree with me because it's a panel that makes things interesting. But my suspicion would be is to find, you know, these specialized hardware units that are low powered and that will do what you want it to do efficiently, and then let the rest of the processor just sit idle.
All right. Well, thank you very much. We have a question from Hamish Carr, and I'm going to read it to you. It's probably a question for all the panelists. Hamish is asking, what trends did we miss or catch late over 10 years of LDAV? Maybe this is a question we can think on for now, unless someone wants to answer right away. Maybe we can try to come back to that question after the last talk, if that's okay with you.
So I think like each of us would give a different, I'll go ahead and try to and Hamish, that's a great question. And one thing that I don't think we've done super great, although I think it depends on other groups have done better. Like Andreas even mentioned this as what seemed like a solve technology was ensemble and uncertainty. Is that I've seen ensemble stuff. I've never been satisfied with all of their solutions in the same way that I can pop a pair view and solve a lot of problems. When I get an ensemble, the first thing is, what am I going to do with this? And I honestly think that road is still a ways down. And in addition to just sort of, you know, having the ensemble is even before you get it is collecting the data, because it's a totally different in situ problem. Like for a normal simulation, which is a one-shot run, you can look at the timestamp and do something. If you're in the middle of generating an ensemble, right, you have such a small piece of the data, you can't do anything with just that. And trying to pull out the information to do, you know, appropriate analysis is hard. And I just don't think that's a solved problem at all. Maybe, you know, Andreas, if you want to, you know, chime in and give a different perspective on that one, but that's something that I have not been super satisfied with our solutions.
Yeah, in general, I can agree, but I think there are some pretty good approaches from weather forecasts. They try to extract probability information, and this is what we are interested in. So it's not just to say, okay, there's an uncertainty, could be -1, could be +1, could be something in between. You have to extract some more information out of that, which is not just one-dimensional. And if you can do that, then you have a benefit of that. If you just have a bunch of ensembles, then it could become a mess. Yeah, you're right.
All right. So I suggest maybe we switch to the last presentation, and maybe we can come back to that question after. And the last presenter is Manish. So Manish, would you be able to share your screen at this point?
That's what I'm trying to do. We have, oh, here it is. Can you see it?
Yes, we can.
All right, so I'll try to keep this brief. So thank you for this opportunity. It's clearly both exciting and timely. My name is Manish Parashar. I wear a few hats that are relevant to this. As a researcher, I would have been excited to present this. I've had a chance to contribute to some of the software that have been talked about. Also, I wear a hat at OSTP, and many of the things that Janine talked about resonated as emerging interagency priorities. Some of you might know I'm taking on a role at the Ski Institute at University of Utah, and I would be excited to talk about all of that, all of the efforts there at some point. But here I'm going to focus on my role at NSF as Office Director for the Office of Advanced Cyber Infrastructure, and I'm really going to talk about how data cuts across many of our programs looking forward. For those who are not familiar with the Office of Advanced Cyber Infrastructure, the U.S. National Science Foundation, this is an office that cuts across the different directorates with the goal of fostering a cyber infrastructure ecosystem for science and engineering research. And we look at both production cyber infrastructure, but also the research cyber infrastructure to enable science. And we have a very broad view of cyber infrastructure. It clearly includes the large computing resources, data resources, networks, but also other aspects such as data and software services, pilots and test beds, coordination, user support, aspects of open access and open science, reproducibility, and of course, most importantly, the people and the organizations, the community. And increasingly, we are realizing that science happens when all these pieces come together. So a big part of our focus is on how can we really integrate these different dimensions of cyber infrastructure towards enabling scientific discovery. And there is a document that outlines our vision, our strategy, and it's online, and you can access it. Focusing on data, right? It is pervasive across many of the things we do at NSF and at OAC. And here's just a sampling of some of the different dimensions of the type of programs NSF has. Clearly, there is research in cyber infrastructure. There is research in building tools, software, services, and other mechanisms, methods to support science. And there is domain-specific aspects of this as well. There is pure fundamental research. There is public-facing aspects such as services, coordination across different data efforts, data expertise, data communities. There is policy aspects. And so we have programs that cut across all of these. I will talk a little more about the last bullet on this, harnessing the data revolution. Some of you might know about 4 or 5 years ago, NSF set out these 10 big ideas. These were forward-looking research problems that would drive NSF's research agenda as well as its investments across all of the different areas of science. One of these big ideas was called harnessing the data revolution, and it was really looking at enabling new modes of data-driven discovery, and that'll allow fundamental questions to be asked and answered at the frontiers of science and engineering. The graphic on the right of the slide sort of highlights the different aspects of it. Outside are clearly applications that cut across the different directorates and offices at NSF. And the core program looked at three basic pillars: foundational systems and CI research, data intensive science and engineering, that's looking at from a domain specific, and education and workforce. And across the over the past few years, we've been building a bunch of different programmatics to support this. For example, data science core, tripods, data intensive science and engineering institute conceptualization awards. And just hot off the press, we just announced this solicitation, which is now looking at the culmination of all these efforts through these large institutes focused on data intensive research in science and engineering. This is, there's a link, well, you can Google the number up there in red, and that'll take you to the solicitation. When I checked this morning, it was still not online, but it should be probably by tomorrow. But again, this is looking at interdisciplinary research institutes that support data intensive science and engineering, both research in the domains, but also in the enabling data science and cyber infrastructure to enable that research, right? So again, this is one example. And just as like all the big ideas, this is an interesting way of the way NSF is doing this. Rather than having, if you know the structure of NSF, it's divided up into 7 directorates looking at different disciplines. However, these programs are are at the director's level, where it cuts across all these things. So it's necessarily interdisciplinary and requires all these different areas to come together towards enabling this research. Drilling down into the Office of Advanced Cyber Infrastructure, I wanted to just say that we are currently in the process of doing some strategic thinking about what our data and software ecosystem is going to look like over the next decade, and what are the priorities for us. We like everything at NSF, we do this with a lot of community input. So on the right of the slide, you see a bunch of different activities we've been doing over the past year and a half or 2 years to get community input. And based on this, on the left are some of the areas that are percolating on top as strategic directions. For example, looking at the interfaces of domain-specific data and software CI and OAC's programs, prioritizing broad accessibility, right? Making data and software CI truly fair, findable, accessible, interoperable, and reusable. And the third one is very important, and it's something I saw through all the other presentations, but balancing this idea of innovation and future concerns with tools that can be used and really enable science, right? So how do you make sure that you couple those cycles of innovation so that you are looking at new methods and new technologies and new concerns, but also being able to build software and tools and infrastructure that is robust enough that the scientists can depend on it and enable their science. And then make sure that we are addressing the workforce issue, which I think at every forum I've been at really percolates to the top. Just to give you some idea of the type of things we have been investing in and are thinking about, right? So here's one, right? So what we've been calling the missing middle. So NSF and all of us have been investing a lot on data sources, whether they're instruments, whether they're repositories, they are observatories, they're large simulations, and they're producing a lot of data. We're also funding methods, infrastructure, tools on the science side, where you can, look at the data, come up with new methods, come up with new tools to do it. And then we are looking at cross-disciplinary, transdisciplinary CI in terms of large computing platforms, large networking infrastructure. However, when you try to connect them together, we often find that it becomes non-trivial, right? The data is too far from where the compute is. Often, if you're trying to use data from multiple sources, it's very hard, if not impossible, to do. And as we go into streaming data, how do you do things like real-time streaming and data fusion, and a lot of issues that really bring these things together when you want to look at end-to-end science, something like like some of the problems that Andreas was talking about, urgent science, which you really need to take streaming data from different models, different observatories, different sensor networks, and be able to enable science in a timely manner, right? And we've already started investing in this, and this is an example of some of the things that we have done. For example, on the left here, you're seeing a way that we've been looking at to leverage resources in the network that are close to where the data source is to be able to transform the data, right? So we have this project led out of San Diego called the Pacific Research Platform. Now it's moving towards the called the National Research Platform. And what they have done is at the entry points in the network, they have these programmable network elements called data transfer nodes. They call them the Fiona boxes, where you can stage data, you can migrate your containers to, right, Kubernetes or whatever you have, you move and you process the data where the data is being produced rather than having to transform it. And they've integrated this across California, and now it's migrating and across the US, and connected them together. And now they're processing data from large wildfire observing sensor networks or environmental observatories, and processing the data very, very quickly. On the right is a project, again, that's looking at the other end, where you're looking at edge networks and making them programmable. And the goal here is to do in situ, but in the wide area, right? So how can you really transform data and enable these data intensive workflows in a more meaningful manner? And again, this is to enable urgent science. I have in here tsunami early warning, and this is really looking at the many sources of data, whether it's land-based or at the ocean floor, that are streaming data, and being able to really combine them in a timely manner to be able to do this kind of tsunami early warning, right? To look at this computing as a continuum and really leverage it towards addressing these workflows. Then finally, I wanted to highlight one of the things, and I think this came up in the earlier talks as well, and this is an area which traditionally NSF has not done a good job at, right, is that we do a lot of funding at different aspects of this translational cycle, right? We do fund a lot of foundational research. We fund a lot of prototypes and test beds, and then we fund production services. However, if you want to really fund this arc where we fund the innovation, but also then allow it to transition into sustainable services that the scientists can use, that's much harder to do. And so increasingly, we've been looking at how do we make that? So if I do some research and come up with a great idea, right, how do I then make it into a tool that a community can use? And then how can I take that tool and then host it on one of our resources or on the cloud, where any scientist can come and use that tool or that service and be able to use it for science? So how do we fund that translational arc and make sure that we can translate all the great ideas that we've been funding into things that directly impact science? And so there's more programmatics on really bridging that arc and providing pathways to production. Finally, a quick note about public access. This is very important, and OAC is really leading this across the foundation. How do we maintain large repositories? How do we make sure that data is open? How do we make sure that we're managing best practices, support open science? And I'm not going to go into detail. I just wanted to point out some of the pointers out here, and I'll be able to take questions on this if you need. But again, there's a lot of effort going on trying to support it both within NSF, but also in coordination through OSTP with the rest of the agencies. With that, I'm going to stop with this slide, which just lists some of the currently open opportunities at NSF that might be relevant to this community. I'll leave this up here, and I will hand it over back to Julien.
All right, thank you very much, Manish, for this very informative and great presentation. Do we have questions for Manish? So I see in the Discord chat that Chris Johnson put a link regarding your new position as a key institute director. Don't see any more questions. Maybe if you guys are up for it, we could come back to this question that Hamish sent on YouTube, and Ken started to provide an answer about the trends that we missed and how to catch late over 10 years of LDAV. And I wondered if any one of you would like to further comment on this.
Machine learning.
Oh, I think Jim spoke. Okay.
Yes, we missed on machine learning. I don't know if I want to go into it, but it's pretty clear that, you know, there's a lot of energy and a lot of, you know, there was a lot of, I do wonder if that was because we weren't gathering data. I do think there's a bit of in DOE there, you know, if you're focused completely on compute and you're not gathering a bunch of data, you can't really learn a lot. And so I do think that there needs to be sort of a, having just watched Manish's talk, you know, I think that it's interesting to me that, you know, people, you know, it's like, you know, you have compute, right? That's X scale, et cetera. It looks like NSF is doing data, but wait a second, you know, clearly if we don't do both of them at the same time, can't walk and chew gum, we're going to have a problem sort of getting to the next level of science because we really know how to integrate these things together.
All right, simple question: how would you view on how to cope this opportunity that was missed? Would you have any ideas to reconcile somehow high performance computing and machine learning for data analysis purposes?
Well, I mean, I do think we need to go through the process of gathering the data. I do not think that so, for example, from experimental science, and in particular, this goes to, I hate to say it, but a lot of these things always come back to the funding models and the culture. So, for example, in experimental science, they build the accelerator, but they don't build the other pieces like the data gathering pieces and all of that. They say, oh, that's for somebody else. Well, the problem is then you're leaving a lot of stuff on the floor. It's more ad hoc, et cetera. So I think that sort of coming to this notion of, okay, where we're building the data, we're putting it in repositories, we're addressing all those sort of philosophical issues that you know, NSF does, you know, the FAIR principles and all these pieces of how do you get data out, how do people use it, that kind of stuff. I think that's all critical. Once you're there, then you can start thinking about how you take that data and start integrating it in and building up a science, you know, a science-oriented thing where you're both doing modeling, you know, simulation modeling, and, you know, sort of validating that with real-world data. And really, that to me is the next level of science. But some of it's going to require cultural and sort of funding changes and sort of metrics that sort of push people in that direction.
All right. Well, thank you very much. So I'm sorry, but in the interest of time, I think we need to move on again. So at this point, I'd like really to thank all the panelists who intervened today in this panel. That was a very dense and lively panel. And as I said before, if you have questions for the members of the panel, please do not hesitate to ask more questions during the week on the Discord server. And we will now switch on to the closing session of LDAV. So I will just ask Manish to stop the screen share, and maybe Christy can jump in. Christy Potter, who is one of the 3 paper chairs of LDAV this year.
Is that working?
You're supposed to have the share screen button at the bottom.
Here we go. Oh, it's not letting me share.
Hold on a second.
Is it working now?
Perfect.
Okay.
Yes.
Great. All right. Well, again, this was a really good session. I appreciate everyone attending and presenting. Very exciting. Glad we could get this done this year. So I would like to thank our best paper committee of Hanwei Shen, Yan Wang, David Thompson, and Wes Bethel. They all put in a lot of effort to do extra reviews for our paper nominees. And so The honorable mention for LDAV 2020 this year is interactive visualization of terascale data from the browser Fact or Fiction by Will Escher and Valerio Pascucci. Congratulations on this really good work. And yeah, here's your document. And then our best paper this year is foveated encoding for large resolutions displays by Florian Fleiss, Matthias Braun, Stefan Frey, Guido Rietner, and Tom Ertl. And again, here is your documentation. And we'd also like to let everyone know that there is a memorial for Dr. Lucy Knoll, who was very instrumental in getting LDAV up off the ground 10 years ago. So please join us on Tuesday. Chris Johnson will be hosting from 2 to 3 Mountain Time. We also have some upcoming events that are probably relevant to some of our attendees, and that would be ISAV 2020. That's on Thursday, and sorry, guys. ISAV 2020 is in November, and EGPGB is co-located with Euroviz, and that will be in June this year. And also we'd like to thank our steering committee, our papers chairs, and our poster chairs for all the hard work that they've done this year, as well as our international IPC. And thank you to everybody who has helped with the logistics of this, including the OC team, the tech committee, the virtual conference committee, the web team, and Patrick Kellenberger from IEEE. Thanks again. Julien, do you want to take it away?
That is it.
Okay.
I was thinking of presenting the last slides, but you did a great job. So that's all good for me. So again, thank to all those who contributed and helped with the organization, and also thanks to all the attendees who contributed to the success of the event. And we hope to see you next year and also in the rest of the week. So have a very nice IEEE VIS, and I guess that is it for LDAV this year. Bye now.
Bye. Thanks, Julien.
Do these three essays construct their argumentation similarly? Where in this table of argumentation data from the previously seen texts can I find certain argumentation patterns? Do these three argument maps depict the same argument? We have developed a visual analysis system for argumentation in essays that can answer these questions at a glance. You want to know how it works? Come to my talk.
VIS is a visual support system for the development of visualization algorithms. It has live compilation, automatic version control, predefined interactions, and tools for visual parameter analysis. By displaying the complete history of the algorithm, users get insights into the correlation between source code changes and visual differences.
White space surfaces are a novel approach to convey depth in vessel visualizations. The core idea is to shift all additional depth cues away from geometry and to use the usually empty space between the vascular structures. This allows us to display functional parameters on the surface and supporting cues on the background. We will explain how to generate such surfaces and how to use them as a canvas to further enhance depth and shape perception.
If machine learning were like education, we would like to test what concepts our student, the model, has learned. Has it learned the concept of object rotation? Does additional text help with object recognition? We need a methodology and platform for conducting such tests. In this paper, we present a novel visual analytics tool that enables hypothesis-based evaluation of machine learned models.
We propose a new semi-automatic method that uses topological features to guide users in tracing neurons, and integrate this method within a virtual reality framework. We use the Morse-Mel complex to find a set of candidate neuron arcs. The candidate arcs are integrated into a VR neuron tracing system and expose through our Morse-Mel complex guided semi-automatic tracing tool. The topological ridge graph underlying our MSC guided tool is robust against gaps in the signal.
Asteroids have always been and will always be a threat to life on Earth. Most likely, an asteroid will hit deep water, but what properties will actually lead to a threat like a tsunami? Ensemble simulations are a common tool to understand the effect of different parameters like the size of the asteroid. We propose an interactive visual approach to help analyzing deepwater asteroid impact simulation ensembles.
Visualizing class separations is used in applications such as classification and clustering. However, many dimension reduction techniques are limited due to the issues of separability and interpretability. We propose a visual analytics framework to support the exploration of nonlinear complex separation structures with the power of locally linear separations.
Pixel Clipper allows visitors to quickly and expressively extract visual clippings from visualizations and add comments to them. The clippings are useful for engaging the public with complex datasets because they are entry points into the visualization. This can be applied in a wide range of engagement experiences, such as the use of facilitated and ambient displays at public engagement events.
Confusion flow is an interactive visualization for the performance analysis of classification models. It introduces a novel temporal adaptation of the confusion matrix, which lets model developers compare the learning behavior of multiple classifiers over time. Find out more about confusion flow in our talk or in our TVCG paper.
Suppose you want to see the overall commit structure of a new project repository. Using Git class tools, GitHub Network, or Git log command is quite burdensome to get overview and navigate data. We presented Gitthrough as an interactive visual analytics system for the Git metadata to help users explore and understand the context of development history.
The classifier trained on the historical data may fail to classify the incoming data when the data distribution is changing. This phenomenon is called concept drift. To handle the concept drift, we developed the Drift VIS, a visual analytics system to help the expert understand when, where, and why the drift happens, and update the model to improve performance.
With the proliferation of AutoML systems, it's now easier than ever for non-experts to create and deploy end-to-end machine learning pipelines. These systems explore the model search space and optimize hyperparameters in order to solve a particular task. We propose Pipeline Profiler, a tool that enables the exploration and comparison of machine learning pipelines produced by multiple AutoML systems. By analyzing these pipelines, we have the opportunity to better understand how AutoML systems work and obtain insights that can be used to improve them.
We propose an interactive ensemble analysis framework that provides flexible interactive exploration of the ensemble data. Time series characteristics of data can be obtained by fast browsing time steps. The region stability heat map view shows the stability of the selected region and provides region adjustment by directly clicking.
CMED is a visual analytics framework for exploring medical image data annotations acquired from crowdsourcing. CMED can be used to visualize, classify, and filter crowdsourced clinical data based on a number of different metrics such as detection rate, logged events, and clustering of the annotations. CMED provides several interactive linked visualization components to analyze the crowd annotation results for a particular video and the associated workers.
How many clusters can you see in these images? With different visual encodings in scatter plots, our perception of cluster count changes. We developed models that consider how visual density influences cluster perception. Further, we demonstrate using a threshold plot to optimize the saliency of clusters.
In our paper, we address the problem of navigating complex multiscale and dense environments, such as these molecular models. We present a technique for browsing a model by clicking on textual labels, which we call hyperlabels. This allows the user to intuitively navigate the hierarchical organization of the model. For more details, read our paper or watch the talk.
While meetings are an essential part of everyday business life, most calendar visualizations are not designed for retrospection. We present a tool consisting of 4 coordinated views that integrate into the user's daily workflow and are designed to promote self-awareness about past scheduling decisions. We discuss the insights gained from an internal user study and from a field deployment. We also discuss how we strongly inherit from the principles of personal visual analytics despite targeting a professional environment.
Hands-on cybersecurity training represents a domain where visual analytics can significantly improve the impact of teaching process. We describe this new application domain and introduce a conceptual model that can serve as a framework for the development of analytical visualizations. Unified training lifecycle will be discussed from the perspective of different user roles.
Progressive visual analytics provides intermediate leisures in the middle of computation to address a long computational delay. However, such intermediate leisures are uncertain, so findings from these leisures can turn out to be incorrect for the entire data. In progressive visual analytics with safeguards, we suggest to risk the uncertainty, but we allow humans to leave safeguards every time they risk the uncertainty.
Morse complexes have shown a great utility in understanding the topology of complex scientific datasets. The noise in the scalar field, however, can significantly distort the Morse complex topology. Hence, we study the extraction of Morse complexes for ensembles of noisy scalar fields through their uncertainty visualization using our proposed statistical summary maps.
Text alignment is a fundamental technique in many text-related domains. In this survey, we cover 3 text alignment scenarios: collation task, text reuse detect